Let's look at a little bit more subtle example of a goodness of fit test in action. For this one, we're going to use problem number 2, which is visible on the screen in front of you, and it reads as follows. World Series. Are the teams that play in the World Series evenly matched? To win a World Series, a team must win 4 games. If the teams are evenly matched, we would expect the number of games played in the World Series to follow the distribution shown in the first 2 columns of the following table. The third column represents the actual number of games played in each World Series from 1930 to 2014. Do the data support the distribution that would exist if the teams are evenly matched and the outcome of each game is independent? Use alpha as 0.05 as your level of significance. Okay. Now, when we run a hypothesis test like this, there's always a few things we want to have written down, especially if you're doing an open-ended question on an exam. Let's take a look at what we would record for this one. If you recall, for the goodness of fit test, the generic hypotheses would be as follows. The null hypothesis would be that the fit is good. And so if we contextualize it for this particular problem, it would be that the teams are evenly matched. And the alternative hypothesis, which is what we have to have at bare minimum for full credit on an exam question as an example, the generic alternative is that the fit is not good. And again, if we contextualize it for this particular situation, it would be that the teams are not evenly matched. So let's see what we were going to be keying into our calculator here. You can see in the upper left corner the columns that the problem was referring to. So we have the number of games, we have the probability, and we have the observed frequency. Now, is it possible that they're trying to goof on you a little bit here by putting things in an unusual order? I would say yes, it is. Normally, if you recall, when we do a goodness of fit test, we want to have our observed counts in list 1 and our expected counts in list 2. So we've been given the observed frequencies last, and we're going to need to put those in first, and then we're going to need to convert that probability distribution to mesh with the sample. Now, if you run the tally of games, 16 plus 17 plus 19 plus 32, you realize that there's a total of 84 games. So we have a probability distribution that needs to be scaled to mesh with a sample size of 84. And let's look at how that's going to take place on the calculator. Now, if you want to follow along, I would invite you to pause the video, and you can key in your observed frequencies here into list 1, and you can key in the probabilities into list 2. We don't actually have to bother keying in the number of games. It's understood from the position of the data in the list. Now, as you can see here, I've got everything keyed in as I said. So I have my observed counts in list 1, and I have my probability in list 2. I'm going to convert list 2 to mesh with the sample size of 34 as follows. So you go up to the top of list 2 and make sure that's lit up. And then you're going to take list 2 and you're going to multiply by 84. And so now you have your counts. And you can see on the face of it that there is some disagreements, but whether they are significant or not, that's going to be up to the test. Now, I'll run the test as before. I'll do the TI-84 and later models version first, and then at the end of the video, I'll show you the workaround method that you could use for whatever model of calculator you're running. So what you want to do is get out of here, and you want to go back to the Stat menu, and you want to go to the Test submenu, and you're looking for the chi-squared goodness of fit test. So we have our observed counts in list 1, our expected counts in list 2. The only thing we need to work out is our degrees of freedom. Now, if you remember, the degrees of freedom is always 1 less than the number of counts being compared, and here we're comparing a total of 4 different categories. So our degrees of freedom would be 4 minus 1, otherwise known as 3. Let's run the test, and we have our result. So we have our test statistic, we have our p-value, and we have our contributions, which you're going to be seeing again when we do the TI-83 version of the test. Let's record these. So again, you can see our test statistic and our p-value. And again, when we're writing an exam problem, for example, an open-ended question, we want to make sure to record certain things. So we definitely want to have the test statistic, and we definitely want to have the p-value. That is, unless you're using a rejection region to run the test. I really don't care whether you use the classic method or the p-value method, as long as you record everything that I need to gauge whether or not you know how to run the test correctly. So here we have what we got from the calculator, and you can actually see what we're going to conclude here, because the p-value is larger than alpha. And so alpha was given in the problem as 0.05, and since the p-value is larger, we cannot reject the null. So on a practical level, what does that mean? Well, it means that the evidence we have shows that, well, it means that we can't conclude that the teams are not evenly matched. That's always the best way to say it. We don't accept the null because we're assuming it true as part of the process. So we can fail to reject, in which case we would say it as we did. It's never a bad idea to put down your practical conclusion from the test as well. And that is a reasonable conclusion. Let's see how this test would look if we were running it on the TI-83. Now, if you recall, when we run the test on the TI-83, we have to construct the test statistic by hand. And so it's helpful if you have an idea of what it looks like. And so as you can see here, we're going to be taking the observed minus the expected. We're going to square that quantity. We're going to divide it by the expected, and then we're going to add up the results. And so when you do that on the TI-83, it looks like this. You're going to go back to your stat menu, and you're going to go back to your lists, and you're going to need a total of 4 lists in order to pull this off. So you go to list 3, go up to the top as you see there. You want to open up a couple of parentheses, and we're going to take observed minus expected. So list 1 minus list 2, close that, square it, close it, and then divide that result by list 2. And it's going to populate the list automatically with the contributions that were on the screen previously when we ran the test using the built-in function. Now we're going to build our test statistic in list 4. And so again, you need to go up to the top of the list, and you would then go to the second stat, which is the list menu, go to ops, and we want number 6, which is a cumulative sum. And we're going to run that on list 3. And so again, you can populate the list automatically. And you can see right down here at the bottom your test statistic. And so that number you're going to need to have written down because you're going to need it for what comes next. And how precise? Well, again, typically I would record it to 3 or 4 places. I think in this case, 6.90476. If I just truncate it at the 1 there, it's going to give me reasonable accuracy, and my answer is going to match what I obtained from the other version of the test very, very closely. Watch how this is going to play out. So again, if you're wondering, what are we doing now? We're going to take that test statistic and we're going to use the calculator to cough up a p-value. Now, if you don't like using the p-value method, you can do the test using the rejection region method, and it's perfectly fine. As long as you write everything down, I'm fine with that. but I prefer using the p-value for obvious reasons. It's much easier to deal with. So remember that value, and we want to quit this, and we need to go to the distributions menu. Now, it's a right-tailed test. We're looking for function number 8, which is the chi-squared CDF, and the syntax would be as follows. The upper limit is always positive infinity, and the way that the calculator would want that would be like this. You'd key in 1, and then you'd press scientific or exponential notation, and then to the 99 power. And so that is 1 times 10 to the 99. That's what the calculator uses for positive infinity. Degrees of freedom, if you remember, we were comparing 4 categories, so the degrees of freedom would be 1 less. That would be 3. And we're ready to paste. If you're using a TI-83, you're not going to have that kind of interface. You're just going to get the command, and so the syntax would be like that. And when you press enter, you get your p-value, and it's exactly what we got before. It agrees to at least 4 or 5 places there, something like that. Anyway, the conclusion is the same. So as we had said, our p-value is larger than the level of significance that was provided in the problem, and so for that reason, we cannot reject the null. The evidence does not support the claim that the teams are not evenly matched. Hope that helps. If you have any questions, please feel free to drop me a line.